Hello, good morning. Am I audible?
Yes, sir.
Okay, good morning and welcome to our class on advanced power electronics. Last time we discussed diode clamp multi-level inverter or the neutral point clamped multi-level inverter, and we discussed the one of the control technique, that is a multiple carrier sinusoidal PWM technique. We discussed. Uh, Also, it is possible to control with a space vector PWM and also the a space vector control. And now today, we are concentrating on the second topology, that is a flying capacitor multi-level inverter. Here we are using the capacitors, particularly for getting the different voltage levels. So we are using the switches IGBT and anti-parallel diode. Switch configuration is IGBT and anti-parallel diode, and we use the capacitors particularly for getting the different voltage levels with the help of the switches. Again, we are just concentrating very simple case, that is a three level inverter, and we have shown only one leg here for simplicity. So this is our input voltage to the multi-level inverter. Input voltage to the multi-level inverter is a VDC, and we have seen that in case of this three level, we are having the three voltage levels. A first level is plus VDC by 2, second is 0, and third is minus VDC by 2. That is a VAO, that is the output A with respect to center point of DC. And we require to level VDC by 2. So we have to divide or split the VDC into the two values. So we are using the two capacitors. So these two capacitors, what are named C2, are used to split the DC link voltage. So here voltage across C2 is a VDC by 2. So voltage across the C2 is divided equally. Uh, it is a VDC by 2 upper capacitor and VDC by 2 in the lower capacitor. And now here we have seen one capacitor we are using, that is we can call it a flying capacitor. This capacitor also has a voltage equal to VDC by 2. So all these three capacitors we have shown in this configuration, each is having a voltage will be equal to VDC by 2. We have seen in case of three level, we are getting a three voltage levels for VAO. And here we have seen that whenever upper two switches are on, let us assume that this S1 and S2 are on. So this A point will be coming to the upper, and voltage will be VAO will be plus VDC by 2. So here this A point will come it here, particularly when both switches are connected. So A point will be coming it here, and VAO will be a voltage VDC by 2 across the load. So whenever this S1, S2 are on, then S1 star and S2 star are off. Whereas in case if you want to get a zero voltage, here we are having the two configurations. S1 and S1 star are on. So here how will the path? We'll just trace the path for this. So here we have seen that S1 is on. So current it will start from this S1. Then it will come to the through capacitor. Then through S1 star. Okay, it will be a going to this way. Okay, so here either diode or this, depending upon the direction, it will conduct. So this is the capacitor voltage here. If you see, this will be a plus minus. This is also plus and minus. So here we have seen that these two capacitor voltages, voltage across the C2 and this C1, if you see, they are opposing each other. They are opposing each other. So C2 and C1 voltage, they are opposing each other, and resultant voltage present between VAO will be equal to 0. So this is one configuration when S1 and S1 star are on. Another configuration we will show whenever we are having a S2 and S2 star are on. So let us, S2 star is on, so we are going for this capacitor. Let us start from this. So we are having the S2 star is on. So S2 star is on, and then this capacitor, and then S2 is on, this, and then this. So lower capacitor, with respect to this lower capacitor, if you see the voltage polarity here, this is a plus and this is a minus, and it is again this lower C2, this lower C2 and this C1, again they will come in series opposition, and so the resultant voltage will be a 0. So particularly for 0 level, we can obtain by just adding the two capacitor voltages which are connected in series opposition. So 0 level we can obtain when the two capacitors, one case C2 and C1, upper C2 and C1, they connected in series but they are series opposition. Second configuration for S2 and S2 star, this lower C2 and C1, they will be connected again in series opposition. And here we have seen that again, whenever you want a minus VDC by 2, if you want that, then we are having our S1 star and S2 star, or S1 dash and S2 dash, these switches will be on. So here earlier we have discussed the concept of complementary pairs. This concept is not applicable here. Okay, we can't use the concept of complementary pair because here we have seen that S1 and S1 star are on simultaneously, and because of circuit configuration, this flying capacitor multi-level inverter, we can't use the concept of complementary pairs. So complementary water S1 and S1 star can be on simultaneously, whereas in case diode clamp we are not, this is not allowed. So this is, we have discussed the one leg of the inverter. We can go for similar another three legs. Okay, so this is our three level flying capacitor multi-level inverter, three phase, three level flying capacitor multi-level inverter. We require four switches in each leg, so totally we require 12 switches. We require three capacitors particularly for this configuration. So we can extend this configuration to the higher level. We can next level, we can go for a 5 level. So this is our configuration. We have shown it for 5 level. We have seen the symmetry of this particular circuit. So here voltage, we are having a 5 levels, and so that the DC we have to divide into 4 equal, and so that we require 4 capacitors. So if you see it here, that a capacitor name is given as C4. Each is having all these 4 capacitors. They are of equal magnitude. They are connected in series, 4 capacitors across the VDC voltage. So each capacitor voltage will be a VDC by 4. Each capacitor is carrying a voltage will be equal to a VDC by 4. Now here we have seen it here. Totally we require for 5 level flying capacitor MLI, we require 8 switching devices, okay, per leg. So S1, S2, S3, S4, that will be our upper devices of the leg, and the lower devices we can call as S1 star, S2 star, S3 star, and S4 star. And here we have seen that we are connected one capacitor. C will be a collector of S4 and emitter of S1 star. That capacitor name we can call as a C1. One capacitor we can connect. If you see here, collector of S3 and emitter of S2, we connect the two capacitors, because the voltage level they're coming maybe a double of that. And here S2 collector and S4 collector or S3 emitter, we connect the 3 capacitors here. If you see here, we are connecting the capacitors such a way that here in this circuit configuration, we can say that voltage across each capacitor is VDC by 4. Is it right? So here we connected two capacitors in series here. C2 named, we are named the capacitor C2. We connected two in series because here voltage appearing may be a VDC by 2. Is it right? And here we connect the three capacitors. So each capacitor is VDC by 4. This is VDC by 4, VDC by 4, VDC by 4. So here, very important thing, we can say each capacitor is having voltage equal to a VDC by 4, including the capacitors used for splitting the DC link voltage. Is it clear? So all capacitors, whatever this circuit we have shown, each capacitor having a voltage, approximately voltage VDC by 4. Here we have seen that charging and discharging of capacitor will take place. So maintaining of this capacitor voltage, we have to do a technique such a way that voltage across each capacitor will be a maintained equal to VDC by 4. Any questions?
No, sir.
So this is the one leg of the uh, 5 level flying capacitor MLI. We are having additional similar 3 levels we are having, and we have seen it here already. What are the voltage 5 voltage levels, particularly for this 5 level inverter, that is plus VDC by 2, plus VDC by 4, 0, minus VDC by 4, and minus VDC by 2. That VO voltage, that 5 levels we can have here. We have shown it here. And now let us go for how will be the switching for getting the various levels. So we are having a total 5 voltage levels as we are discussed in case of 5 level. One is plus VDC by 2, VDC by 4, 0, minus VDC by 4, and minus VDC by 2. Now let us go for plus VDC by 2. So when we get a plus VDC by 2, that will be a very simple. We are having, we can get the plus VDC by 2. When your upper 4 devices are on, plus VDC by 2 we get when our S1, S2, S3, I am just showing with the pen here, these 4 devices are on. Okay, so upper 4 devices are on, S1, S2, S3, S4. Then this A point will come at upper DC link. This is our A point, upper DC link. And this VAO will be a two capacitor voltages, VDC by 4, VDC by 4. So VDC by 2 with respect to O, point A will be a VDC by 4. Point A will be, sorry, VDC by 2. So here point A with respect to this point O will be a VDC by 2. So this is what we have shown it here. Which switches will be on? Which switches will be on to obtain the one voltage level, that is VAO will be a VDC by 2, and for that which switches should be on? Upper 4 switches, S1, S2, S3, S4. When this upper 4 are on, lower 4 will be off. So this S1 star, S2 star, S3 star, and S4 star, these switches will be off. Now we are going for, this is the only one, particular for VDC by 2, only one switching state is available. We don't have a alternative switching state. But if we are having a VDC by 4, we want to get a plus VDC by 4 voltage at across the VAO. This is our VAO. This is the O point here. We get it here. So for getting this, there are 3 possible combinations. We have shown it here. Okay, if you look at this, so when we get a VDC by 4 at the VAO, we can obtain by 3 different switching combinations, and that is we can call as a switching state redundancy. This we can call as switching state redundancy. So here VDC by 4 VAO, that can be obtained by 3 different switching states. Any one you can use as per your requirement. So this is the advantage, we can say it will have a redundancy in the switching states. And now we can discuss only one, you can other two. Let us go for, here we have shown this. Let us assume that S1, S2, S3, S1 dash or S1 star, these are on, And now here from O, we have shown it here. So how we get it? S1 is on, S2 is on, S3 is on, S4 is off. So current will go through a capacitor, this, and then through S1 star or through a diode, depending upon the direction of current, it will come to this. So here, how many capacitors will come across the load? If you see it, how many capacitors will come in series with the VAO point? Here we have seen that these two capacitors and this. But we have seen that this capacitor is having the upper terminal is positive and lower terminal is a negative, and this opposes this. So here we are having two capacitors will provide a voltage will be equal to VDC by 4 plus VDC by 4. So that will be a positive VDC by 2. Okay, we'll get from the capacitors for DC split VDC by 2. Whereas this capacitor is having a voltage minus VDC by 4, it will be oppose this minus VDC by 4, and remaining that resultant will be equal to VDC by 4. So this fashion we can get this VDC by 4. A positive VDC by 4 we obtain whenever we are considering the this switching state. So anytime four devices will be on, but not necessarily. Okay, so here we are one configuration we have shown. Similarly, you can try out for the other configuration. So here we can say that we are having for getting a VAO VDC by 4, we are having three switching states are available, and so any one we can use depending upon a requirement voltage balance, and that concept we can call as a switch redundancy. So for obtaining one particular voltage level, we can have a different switching states are possible. That is what we can call as a switch redundancy or state redundancy is available. Whereas for VDC by 2, we don't have a switching state redundancy because only one specific VDC by 2, only we have to switch on these four devices. We have to switch on the four devices. No switching redundancy is available. So here we are having a second level. So we discuss the VDC by 2, VDC by 4. Now let us go for zero voltage. And if you see it here, particularly for zero level, we can get by possible 6 combinations we can have. Okay, we have shown it here. For getting a VAO voltage that will be equal to 0, it means that how many switching states are possible? We are having a six switching states are possible. So here switch redundancy is, or the switching state redundancy is there. Any one we can use. Now let us consider here first S1, S2, S1 star and S2 star. So here we have shown it here. Let us consider we are having a S1, S2 is on, and S1 star and S2 star, these are on. And we have shown it, we started tracing from O point, these two capacitors. Okay. Then we can have a switch S1 and S2. Then we are having these two capacitors, C2, named they are the C2. Okay. And then through the switches or darts, depending upon the current direction, then it will be going to the load, and this point and this point is same. So here we have seen that these two capacitors that is named C4 and these two capacitors named C2, these two are in series, these two are in series, each is having a equal voltage. Each capacitor is having how much voltage? Each capacitor is having a voltage will be equal to VDC by 4. These two are additive, these two are also additive, but these two and these two, C4 opposing the C2. So because of that, net resultant voltage will be a 0. So voltage across this C2 capacitor is VDC by 2. Voltage across this C4, both capacitors additional will be a VDC by 2. But they are in series opposition, and because of that, we can get the 0 voltage. We can get the 0 voltage. This is a particular case we can have. Similarly, we can show here another case will be a S3, S4, S3 star and S4 star. So let us we can just trace this particularly for second case. So we can start S3, S4. So here these two are on. So S3, S4 are on, and S3 dash and S4 dash is on. So we can start it here. So lower side of this. Okay, so we'll go for this S4 and S3 star. Then through these capacitors we see again we are coming the same two capacitors, C2 capacitors, through these two C2 capacitors. Then our S3 and S4, S3 and we are having S4 and going to this. Again this C2 and this lower two, what are these two capacitors? Okay, I'm just showing it here. I'm just mark the okay current path direction. So particularly for second uh, switching state, you can call as here S3, S4 are on, these two are on, and S3 and S4 dash are on. So we start from negative DC rail. Okay, we start from negative DC rail. Then we are having the two switches S3, S4 dash, S3 dash, or S4 star, S3 star. Then these two capacitors named C2, and then we are having S3 and S4, and then this. So path we have traced with the red line, and we have seen that again these two capacitors named C4 and these two capacitors named C2, again their voltages are opposing each other, and because of that we'll get the VAO will be a zero. VAO will be a zero. So this is a particular case we get when our VAO is zero. Other we are having almost four. Similarly, you can just trace out and see how we can get the. So just here addition of the capacitor voltage is done, and so the two voltages. So definitely other two voltages will be a subtracted, and so that resultant capacitor voltage comes out to be a zero. So here capacitors are connected in series such a way that the resultant voltage will come out to be a zero for this. So C2 voltage, this voltage will be VDC by 2, this C4 2 capacitor voltage VDC by 2, but they are connected in series opposition. So we get the voltage level as the zero. Now similarly, now we can go for a minus VDC by 4. It is a very simple case for minus VDC by 4. So minus VDC by 4, our lower four devices are on. So minus VDC by 4, these four devices S1 star, S2 star, S3 star, S4 star are on. So this will be our particularly we are having this will be on. These lower four devices will be on. S1 star, S2 star, S3 star, and S4 star are on. And we get that this voltage across these capacitors will come across the load, and we get the voltage will be equal to a VDC by 2. This is having a unique switching state for plus VDC by 2 and minus VDC by 2. We don't have a switch redundancy, particularly for plus VDC by 2 and minus VDC by 2. Now let us go for last switching state of this 5-level flying capacitor multi-level inverter is a minus VDC by 4. And again for minus VDC by 4, a possible three switching states are there, three switching combinations are possible. And one of that we have shown it here. One of that let us go for first. Okay, so S2, S3, S4. So S4, S2, S3. So these we have shown it here. This will start from this, then S2, S3, or we can have S4, S3, S2, and then S4. And then we are having a. So let us go for VDC by 4. So here S4. So here S4, okay, this is we are going for this gate. So whatever we trace is from this O point through these two capacitors, then these three switches S2 star, S3 star, S4 star, or S4 star, S3 star, S2 star, then this capacitor, and then S4 switch, and then this. So here these two capacitors addition will be VDC by 2. This capacitor is VDC by 4. So VDC by 2 minus VDC by 4. So we'll get the VDC by 4 at the load. Similarly, you can just make the sketch particularly for other configurations also. So what will be our observations? So here, first observation, if you see it here, particularly a first observation, multiple switching states are available. Okay, we are available multiple switching states for minus VDC by, sorry, minus VDC by 4, 0 and plus VDC by 4. That we are having a multiple switching states are available, but they are not available plus VDC by 2 and minus VDC by 2. Here, a proper selection of switching state, a capacitor voltage can be balanced. That is advantage of this particular configuration. Whereas dark lamp multi-level inverter, whatever a DC link capacitors, if you just go for here, whatever configuration we have studied last time. So here, if you see it here, we are in 4 capacitors, and under normal operating condition, balancing of this, whatever conventional technique we have discussed. Which technique we have discussed? Multiple carrier sinusoidal PWM technique we have discussed. With this particular technique, it is not possible to balance the voltage across these 4 capacitors. There will be a special techniques are required to maintain this. So this is a drawback of particularly neutral point clamped inverters, that balancing the capacitor voltages. But here, this will be we can say that we are having here provision is there. Here provision is there. We are having a multiple switching states are there, and based on that, it is possible to balance the capacitor voltage. Now clamping capacitors, whatever these capacitors require, these capacitors, excluding the capacitors required for splitting the DC link, that will be different. This is only 4 for total, but here we are in a one leg will require how many? This 5 level will require how many capacitors? 6 capacitors per leg. So here clamping capacitors per leg. Let us take the example. We are having a 5 level multi-level inverter. M is the level. So a 5 minus 1. So it will be a 4 multiplied by 5 minus 2. So I'll directly 5 minus 2 will be 3 and divided by 2. So here 12 divided by 2 means it will require 6 capacitors per leg for 5 level multi-level inverter. So and we have seen that here we require 6 capacitors particularly for the 5 level multi-level inverter. So here M we can take as a level 5, put a 5, then we will get the 6 capacitors per leg. So totally we require 18 capacitors. And the size of capacitor will depend upon the load current. Okay. So here, one of the drawback of this configuration, you can say, one of the drawback of this configuration is a excess storage capacitors are required. We require capacitors, and capacitors are bulky, load currents are more, than value of capacitor will be also more. So this will be excessive number of storage capacitors, bulky capacitors are required. That may be a disadvantage of this configuration. But here switch combination redundancy can be used for balancing the capacitor voltage. And with all these constraints, our inverter control will be complicated as compared to a diode clamped multi-level inverter, as compared to a diode clamped multi-level inverter. So now this is all about our 5 level diode clamped, sorry, 5 level flying capacitor multi-level inverter. Any questions?
Sir, how do we ensure that each capacitor has a voltage of VDC by 4 across it in 5-level multi-level inverter?
Here, okay, so that is the main question, is it? Our control will be a very complex. Okay, control will be a, so we have to okay, once we have to simulate this. Okay, we have to refer the paper, whereas we are not taking the control of this particular 5-level flying capacitor multi-level inverter. We are not taking the control of this. We have to refer the paper based on this, and we find out that how here zero switchings. Okay, we are having a, if you want to a zero, but with zero we can use which capacitor is voltage is not maintained constant, and can you maintain that voltage constant with the appropriate selecting of the switching state. Okay, so we have to find out new techniques for this. Okay, I will make the update and you tell you, but papers are available, you can just search on this, and it is possible by just switching state redundancy, it is possible to maintain the balancing of the capacitor voltage. Here what configuration we have shown it here is three capacitors, we have shown it here two capacitor one. Our assumption is that each capacitor is having a voltage will be equal to vdc by 4. Okay, vdc by 4, and that is why we are selecting these capacitors particularly this. Okay, so we require a more complicated control, and with the help of that it is possible to maintain the, okay, balancing of the capacitor voltage. Okay, you refer the, just we have to refer some papers. Okay, this is not a part of our syllabus. Okay, we have to take the update and we have to just see that balancing of capacitor, is there any techniques are available for the switching of this. Particularly in lab simulation, we are taking the diode clamped multi-level inverter, and also we are going for cascaded H-bridge multi-level inverter. But we are not going for the control technique for this flying capacitor multi-level inverter. If time permits, okay, we will try for this. Okay, PWM switching of 5-level uh, flying capacitor MLI. Is it okay? So we have to refer papers. At present, I don't have the latest update, but okay, definitely in the succeeding lectures, I will try to provide this, or at least I will find out paper and I will send to you the paper regarding the uh, how to control the flying capacitor MLI. Any other question? Any doubts?
No, sir.
Okay, so this will be our second topology we have discussed, and now we are going for next topology, that will be our cascaded H bridge multi-level inverter. Okay, you can call as MLI. So our next topology, that will be last topology in the multi-level inverter, is a cascaded H bridge multi-level inverter. What you do understood by a H bridge? What is the meaning of H bridge? In our case, H bridge is nothing but a single phase full bridge inverter. So here, a meaning of what we want to say here, uh, H bridge. This H bridge is nothing but a single phase bridge inverter. A single phase bridge inverter that we can call as a H bridge. Now, if you see it here, what you are observing here, if you look at the circuit, if you look at the circuit, up till the inverters we are discussed, we are having only one DC source. Is it right? Only one. Either a this flying capacitor multi-level inverter. We are having only one DC source. We split with the help of capacitor, but only we require a one DC source, input DC source for a flying capacitor multi-level inverter. Similarly, we require only one voltage source in case of a diode clamped multi-level inverter or neutral point clamped inverter. But here, if you see it here, for each phase or for each H bridge, this is the four devices: IGBT, anti-parallel diode. These four devices we can call as a H bridge, single phase bridge inverter, that we can call as a H bridge. So here we are having one power supply for each H bridge. That is a drawback of this, you can call it the cascaded H bridge. Cascaded H bridge inverter. Basically, we requires a separate power supply for each H bridges. Here we are having one bridge per phase, and here we word use cascaded. That means we require more number of H bridges we connect in series. More number of bridges we connect in series. Here we are not shown. We have shown a one bridge. Here we have just shown a one bridge here per phase. But here you cannot word use a cascaded. So whenever we require more number of H bridges in series per phase. Here we have seen that this is the four switches: SA1, SA2, SA3, SA4. This is for A phase, where input is the VDC and load is connected as phase, single phase load is connected this across this one H bridge. Another we are having another single phase H bridge, and we connect a B load across this. It is supplied from a separate DC supply. Third, for a third phase, we are having a one H bridge, and it is supplied from a separate DC supply. So each phase is supplied with a separate H bridge. Now here this one phase is supplied with a one H bridge, and this H bridge, particularly a single phase bridge, full bridge, single phase full bridge, has a three switching levels, three voltages we can get it across this. How we get this? Let us, we are having a SA1 and SA2 are on. So this is the upper terminal we consider only for phase A. Same case will be for the other two. So we are considering the upper bridge. This upper terminal is positive, and let us assume that SA1 and SA2 are on. So this plus VDC will come through this switch. You see it here. Through this switch, plus 1 will come to the point A, and through S2, okay, this will be just, we are drawing it here. So this will be a, when S1 and S2 are on, or SA1 and SA2 are on, this is our path of current. We have shown it here. So when SA1 and SA2 are on, when SA1 and SA2 are on, we see that A point is connected to plus VDC and minus point is connected to the neutral. So our VAN, that is here phase to neutral voltage. Not here we can call it as a node voltage concept or pole voltage concept. Okay, here now we can call as the a phase voltage. We are star connected load. Here we are having a star connected load, and this is a VAN, a phase voltage. When SA1 and SA2 are on, our VAN will be a plus VDC. So when SA1 and SA2 are, our VAN will be plus VDC. You have seen it here. Now whenever upper two are on, S1, S3 are on, I will use a different pen here, color. So whenever S1 and S3 are on, we have seen that our load will be a shorted. I will just show it here. S1 and S3 will be on. Our load will be a shorted. Okay. Through these two devices, our load will be a shorted. Load will be a shorted, and or whenever lower two are on, whenever the lower two are on, again our load will be shorted, and when load is shorted means VAN will be a 0. Okay, so load will be shorted whenever our two upper switches SA1 and SA3 are on. Our load will be shorted when SA4 and SA2 are on. So this is the case. And now the VDC we can obtain when SA3 and SA4 are on. So whenever this so let us go for this. Whenever these two are on, I will use the highlighter here. So whenever, let us assume that our SA3 and SA4 are on. So whenever SA3, if suppose this will be on, and then here we are through this. So now our neutral point is connected to positive. Neutral point is connected to the positive, and A point through this switch SA4, it will connect it to the negative of this. Okay, and because of that we'll get the minus VDC. Because of that we'll get the minus VDC. So here one H bridge will provide how many levels? One H bridge will provide how many voltage levels? Am I audible? One H bridge will provide how many output voltage levels?
3.
So one H bridge will provide three output voltage levels. And what are these three output voltage levels? Plus VDC, 0, and the minus VDC. So this is the case for particularly three voltage levels in the phase voltage, and that's why we can call it as a three level. Similarly, the switching will be for the a second leg, okay, and then again we can get a three levels and third, and we have to maintain the phase shift of 120 degrees between the phases. So we are having the independent control of each phase, is it right? Here one phase is controlled independently, another phase is controlled, and this, and each phase has a supplied, or each H bridge is supplied with a separate DC supply. So very, very important in case of cascaded H bridge multi-level inverter is each H bridge should have a separate DC supply. And now let us go for how to get the 5 level. Now cascaded H bridge with a 5 level configuration, 3-phase 5 level. And now here, if you see it here, two H bridges are connected in cascade. This is one H bridge, okay, and this is another H bridge. They are connected in cascade. So two H bridges will be connected in series to get the 5 levels. Two H bridges, here we can say we are connected the two H bridges in series to get the 5 levels. So one bridge will give a 3 level and other bridge will give a 2 level. So here whenever we connect two H bridges, then we get a 5 level. So first bridge will give a 3 levels, other bridge will give a 2 levels. Now suppose I connected 3 bridges in cascade. Let us assume that if I connect the 3 bridges in cascade, 3 H bridges I connected in 3 H bridges, I connected in series, cascade. So what will be the level of the phase voltage? If I connect 3 H bridges in cascade or in series, then what should be the number of levels in the phase voltage?
7 level.
7 levels, correct. So only first bridge will give a 3 levels, and if you go on add the one bridge, it will add the level by 2. It will add the level by 2. So here a first bridge, here a first bridge will give the 3 levels, and next consecutive bridges will give only a 2 levels. So this is 3 plus 2, 5. If you add another, then we get another bridge, 2 levels, again another 2. If you are having the 4 bridges in cascade, then we get the 9 level. If 3 bridges in cascade, we get a 7 level. If 2 bridges in cascade, we get a 5 level. And one bridge only, what is the configuration we have seen here? Is one bridge, it will give a 3 level. So in particularly cascaded H bridge, we are having either 3 level, 5 level, 7 level, 9 level, 11 level. All we can get the odd number of levels. All odd number of levels. The even number of levels are not possible, you can say it here. So even number of levels are not possible in case of a particularly the this cascaded H bridge inverter. So now here we have seen that for 5 level, how many DC voltage sources are required? For 5 level, how many DC voltage sources are required?
6.
6 DC voltage sources are required. So that we can say it will be a limitation of this H bridge. This we can say it will be a limitation of this particularly H bridge. Each cascaded H bridge multi-level inverter limitations is that, or drawback is that, we require more number of DC sources, and number of DC sources will be equal to number of H bridges. Here 3-phase 5-level cascaded H bridge multi-level inverter, we required a 6 bridges, so we require a 6 separate power supplies. We require a 6 separate power supplies, and this may be a beneficial in some applications. This particularly number of DC voltage sources are may be very easily obtainable in some cases, and this one may be in case of our solar PV. In case of a solar photovoltaic, we are having so many number of panels, so we can make a group of panels to get the VDC. So we can say that this configuration may be a possible application of this configuration, may be a solar inverter. So solar inverter, one of the possible configuration is the cascaded H bridge inverter, because we are having so many number of panels present for the particularly solar, and in that case make a group of panels to form the VDC, and so that it is very easily we can have a separate DC sources are available from the solar PV. So this may be a possibility, one configuration we can get for this. Now here, if we are just given how to obtain the 5 levels here. Now here, this is a 2 bridges in cascade. So this is a VDC and VDC. And now here, at the output, whenever we are getting the addition of these 2 voltages, then we can get the, whenever this upper and lower VDC are added together, series addition is there, added together, then we get a twice VDC. One level will be a twice VDC whenever these 2 DC bridges, DC sources are coming in series across the load. Whenever this VDC, you can call it as a 1 and 2, you can give it the name. So this is a VDC 1, this is a 1 source, and this is a second source. They are added together and they will come across the load. Then we are getting the level will be equal to a twice VDC. So one level we can obtain for 5 level will be a twice VDC. So when we get a twice VDC, these 2 voltages are added, and with respect to neutral, this will come out to be a positive. Then we say that we get a plus VDC. When we get similar line, when we get a VDC, only VDC, so only one source out of these 2, only one source will come across the load with the switching. Only one load will come across the switch. Only one source will come across the load. Whenever only one source will come across, either lower or upper depending upon switching. If only one source is coming across the load, then we'll get a VDC. One source is not taking part at all. Whenever 2 sources, they are connected in series and they will come A terminal positive with respect to N, then we get a plus VDC. VDC of this plus VDC, both are in series additive, then we get a twice VDC. Whenever only one DC source will come across the load with the switching, then we get a VDC. Similarly, whenever we are having only one DC source will come in opposite polarity with the load, means neutral will become positive and remaining terminal will become negative, then we get the VDC. And if 2 sources with opposite polarity, they will come across the load, then we'll get a twice VDC. Now when we get a 0 voltage level with the same logic, when we get a 0 voltage, so here we discuss whenever 2 voltage sources, these are 2 voltage sources added together and come across the load with positive polarity, 2 VDC. When one source is coming across the load with positive polarity, then it is a VDC. When one source with negative polarity is coming across load, minus VDC. And when two sources will series but coming negative polarity across the load, that is a minus VDC. And when we'll get a 0? When we get the voltage level 0, anybody? For getting this plus VDC, these two sources are added together. VDC, their polarities will be series additive whenever twice VDC we are getting. But when the polarities are opposing each other, so these two VDC sources, they will come across the load, but they will come in series opposition, and resultant voltage across the load will be 0. When they are coming in series opposition, then resultant voltage will be a 0. Now here we have shown the switchings of this. Okay, here we give name with a specific, particularly this SA1, if you see it, SA2, SA3, SA4. We'll give the same names as that of diode clamped multi-level inverter. And our intention is same control technique can be used for cascaded H bridge. So lower bridge, we are giving the switches as a SA1 and SA2. Here in case of cascaded H bridge, we are having the concept of complementary pairs. So SA1 and SA1 star, they will be a complementary pairs. Out of that, only one will be on. Similarly, SA2 and SA2 star, only one will be on. SA3 and SA3 star, only one will be on. And here SA4 and SA4 star, only one. So complementary pair concept is applicable to a diode clamp multi-level inverter, and it is applicable to a cascaded H bridge multi-level inverter, but it is not applicable to flying capacitor multi-level inverter. So remaining part, okay, so we require more time. So tomorrow we can discuss the remaining part of the cascaded H bridge multi-level inverter. Now, what should be a convenient time for our test? So we have to discuss the test. So
1:30. 1:30 today.
1:30. It is a 30-minute test. Okay, we checked the answer books and the result. I am not happy with the result of this particular case. Okay, very few students are scored good marks. Others are just pass and slightly higher than this. Then what is the problem? What was problem? Why you are not scored good marks in the particular test one? What is the reason?
So paper was so lengthy, sir.
No, it was not a lengthy. We have to write it here. We are required just 8 objectives. Okay, 8 multiple choice questions. How many? It will require just 10 minutes to do this. Bad luckily, if any one of them may be getting a numerical problem, that may be okay, require some time. But hardly 10 minutes will be required to just complete the multiple choice question. And remaining whatever we are having, almost 50 minutes are available for 4 questions, and they are very simple, not necessary to write it. Okay, briefly what are required, you have to just write it, but that was not done it. Okay, so maybe your placement and this, but you take next test, that definitely you have to score more, but test will be also similar pattern, lengthy, and it will be tricky. Okay, so you should prepare from that point of view. Okay, so that your grade will be better in the overall case. Okay, so you can go for better. I think that you will get a good marks in the test too, but for that you have to be prepared. Okay, without okay preparation, it is not possible to get. But I find out very bad scenario, question number 5 and 6. Some people has coming as question number 5, thus others the same question is question number 6. The descriptive questions, okay, they are Okay, just interchanged. But the students who are blindly copied, a lot of cases are there. They are written the question number 5, but that answer is of question number 6. They are written question number 6, but answer is question number 5. What we can do for this case? Is it a clear evidence that at least you are not seeing what question is there and what answer I am writing? Is it a few cases are there? I have given the marks considering due consideration, but it will clearly indicate that you are making a mass copying it, but you are not also observing whether the question number is right or wrong. Okay, we are given just question number 5 and 6. Similarly, 11 and 12. They are just flipped. Okay, some people 11 is 12 and 12 is 11. But while writing answers, it is not the correct way. I have considered this, okay, all pandemic and this given this. But next time this happens, definitely will give the 0 marks this type of this. At least you have to see that is the what I am writing. At least you can just take a question and answer. You are blind about that, what you are writing about that question. That is 4-5 cases I observed, but okay, fine this time. So okay, so we'll meet at
Sir,
1:30. S will be just for 30 minutes, and time constraint is very, very important.
sir, can
Okay,
we
if
take
you
the test
submit
at
late, you will get definitely very less marks. So you should be ready on the toes. Whatever completed, not necessary to complete all. That is first thing. We are having the 30 questions. Whatever you are knowing, you can write it. Not necessary to complete that. I have to complete 30 and then submit. Not necessary. So your time is very important. Before 30 minutes, we'll start at 1:30 and test will be end at 2 p.m. So you should be very careful while submitting the test. Okay, thank you. So we'll meet at 1:30.
Sir,
Thank you.
sir.
Yes.
Can we take the test at 1:15 to 1:45?
1:15. Huh.
Because we some students have another test at 2 p.m. for campus.
Okay. So 1:15 we can start. No problem.
Okay.
1:15 and then 30 minutes. 1:15 to 1:45. Okay. Okay, fine. So meet at 1:15. Okay, thank you.